All right, let's talk about one of the absolute cornerstones of building any system that needs to scale, replication. On the surface, the idea is so simple, right? Just keep copies of your data on different machines. But the devil is really in the details here. Getting the how and the why right is the difference between a system that can handle anything you throw at it and one that just falls apart when things get real.
So here's how we're going to break it all down. We'll start with the why, the fundamental reasons this is even a thing. Then we'll get into the most common model, leader-based replication. After that, we'll peek under the hood at the replication logs themselves and tackle the biggest headache, lag. From there, we'll explore some wilder architectures like multi-leader and leaderless systems, and we'll wrap it all up by looking at the big trade-offs you have to make.
Okay, first things first. Before we even get into the weeds of how this stuff works, we've got to ask the most important question. Why? Why do we go through all this trouble? Why not just get one really, really big computer and call it a day?
Well, it really boils down to three unavoidable truths. First, latency. If your users are in Japan and your data is in Virginia, physics is working against you. You have to move the data closer to people to make things fast. Second, availability. Look, machines fail. It's not an if, it's a when, and your entire service can't go down just because one server did. And third, throughput. You can only hit a single machine with so many read requests before it just gives up. You need to spread that load across multiple copies.
So, knowing why we have to do this, let's look at the most common how. This is leader-based replication. You might have also heard it called master-slave in the past. It's really the bedrock of so many databases we rely on every single day. The idea behind it is actually pretty elegant. One node gets to be the boss, the leader. Every single write, whether it's an insert, an update, or a delete, has to go through that leader. The leader's job is then to record these changes in order, creating a kind of change stream, and broadcast it to all the other nodes, the followers. This gives you a single source of truth, an official history of what happened and when.
And right away, we hit our first huge decision point, synchronous versus asynchronous. This all comes down to a simple question. When does the leader tell the client, yep, we got your data? With synchronous, the leader waits. It waits for at least one follower to raise its hand and say, I've got it too. This is awesome for durability. You know for a fact your data is safe on at least 2 machines. But the user is sitting there waiting that whole time. Asynchronous is the total opposite. The leader gets the write and immediately tells the client, we're good. It's incredibly fast. But now you have a window of risk. If that leader crashes a split second later, before it managed to tell the followers, that write is just gone. Poof.
So how do you add more read capacity to a live system? Well, the process for bringing a new follower online is actually super slick, and you can do it with zero downtime. First, you take a consistent snapshot of the leader's database. You then copy that snapshot over to your new follower machine. That new follower then connects to the leader and says, hey, I have the data up to this point in time. Can you please send me everything that's happened since? It then chews through that backlog of changes, and once it's all caught up, boom, it's live and can start serving reads.
Now this is where it gets dicey. Handling failures. If a follower goes down, honestly, not a big deal. It just comes back online and asks the leader for whatever it missed. But if the leader fails, now we're in a high-stakes situation called failover. The whole system has to agree the leader is dead, elect a new one, and then reroute all the write traffic. It's a really delicate process. And if it goes wrong, you can get something called split brain, which is just as bad as it sounds. That's where 2 different nodes both think they're the leader, and they start accepting writes independently. You end up with 2 conflicting versions of reality, and cleaning that mess up is a nightmare.
You've heard me mention this replication log or change stream a few times now, but what is it actually? What's inside that stream? Because the format you choose has huge, huge implications for everything from performance to how flexible your entire system is.
So, there are a few different flavors. You could just send the raw SQL statements. It's super compact, but it's brittle. What happens if you use a function like now? The followers will get a different timestamp. Another way is to send the low-level write-ahead log, or WAL. This is basically the raw bytes that get written to disk. It's super high performance, but it ties you very tightly to a specific version of your database engine. The most flexible approach is a logical log. It describes changes like, this row with this ID had these fields changed to these new values. It's perfect for things like change data capture, where you want other systems to be able to consume these events. But the downside, the logs can get pretty big. And finally, you could use triggers to build your own log, which gives you all the flexibility in the world, but it's often slow, complex, and super easy to get wrong.
All right, let's talk about the single most common headache you're going to face with any async system, replication lag. It's that tiny delay between when a write hits the leader and when it actually shows up on a follower. It's the reason we have the term eventual consistency.
And we've all felt this.
This is the classic drives users nuts scenario. You change your profile, you hit refresh, and your old info is still there. Your write went to the leader, no problem, but your page reload, your read request, got sent to a follower that was just a few milliseconds behind. It hadn't gotten the update yet. We call this a read after write consistency problem, and from a user's perspective, it just makes the app feel broken.
So how do we fix this without giving up the performance of asynchronous replication? Well, we can offer stronger guarantees that make things feel more intuitive. The big one is called reading your own writes. The logic is simple. If a user just wrote something, make sure their next read comes from the leader or a follower that's definitely up to date. Another is monotonic reads. This just ensures a user never sees time go backward, like seeing a new comment and then having it disappear on a refresh. And finally, consistent prefix reads. Make sure that related events are seen in the right order.
Up until now, we've been living in a world with just one leader, one king. But what happens if we break that rule? This is where we get into some more advanced and way more complex architectures that are built for very specific, very demanding situations.
So imagine this, a multi-leader setup. You could have a leader in a data center in Europe and another one in North America. Both can accept local writes, which is amazing for performance. This is also great for apps that have to work offline, but it introduces probably the hardest problem in all of distributed systems, write conflicts. What happens if two people edit the same document at the same time in two different places? You now have two valid, yet conflicting versions of the truth, and your system has to have a way to resolve that.
Now let's take it a step further. What if we just got rid of leaders altogether? This is leaderless replication, an idea made famous by Amazon's Dynamo paper. In this world, any replica can accept a write directly from a client. This design is all about maximizing availability and fault tolerance. As long as you can talk to any of the nodes, you can write to the system.
So how does this even work without a leader to keep order? The secret sauce is a concept called quorums. So let's say you have n total replicas. You decide that a successful write has to be acknowledged by W of them, and a read has to get an answer from R nodes. The magic formula is this. As long as W plus R is greater than N, you are mathematically guaranteed that the set of nodes you read from will overlap with the set of nodes that got the last successful write. It's a really powerful way to tune your consistency on the fly.
Okay, we've gone on quite a journey here, from the simple single-leader model all the way to the chaos of leaderless designs. So, how on earth do you choose? Let's put them all side by side and see what we've got. This is really the whole game, right here. Single leader is simple, it's consistent, it's easy to reason about. But that leader is a bottleneck and a single point of failure. Multi-leader gives you fantastic performance across different data centers, but you are signing up for the nightmare of conflict resolution. And leaderless gives you the absolute best availability and fault tolerance, but it comes at the cost of weaker consistency and having to build more smarts into your client. There is no silver bullet. The right answer is always dictated by what your application actually needs.
And I think this quote from Douglas Adams is the perfect way to wrap up. Designing these systems isn't about hoping for the best. It's about knowing all the ways things will go wrong and then choosing a replication model that fails in a way that you and your system can actually handle. That, right there, is the true art of being an architect. Thanks so much for tuning in.